So last class we were discussing about inter-VLAN routing. Inter-VLAN routing using router on a stick has a lot of drawbacks. That's why we have SVI. SVI stands for Switched Virtual Interface. Meaning it's a interface VLAN. It's an interface VLAN. See, I'm not talking about just VLAN. Just VLAN, if you want to create, what you do, you go to the global configuration mode and you type the command VLAN 10. That creates VLAN 10. But what I'm saying now is something called interface VLAN. Interface VLAN 10. What is this? This is interface. This is just a VLAN. Now I create a VLAN and I put this interface. Let's say this is fast Ethernet 0/1 and fast Ethernet 0/2. I put them as what? Switch port mode access, switch port access VLAN 10. So this interface has become member of VLAN 10. Likewise, I make this as a member of VLAN 10. We did it in CCNA. Now, for these two PC, you got an IP address whose subnet is 10.1.1, and you need a gateway. So the gateway for these two PCs are 10.1.1.1, 10.1.1.1. I want this gateway address to be assigned somewhere. Where I will assign? For that, what I do is I create a common interface which belongs to this broadcast domain. For VLAN 10, you may have hundreds of interfaces in VLAN 10. But for all those 100 interface, there is going to be one logical interface or interface VLAN, and that interface will act as a gateway for all these VLAN 10 member. Because I say VLAN 10, interface VLAN 10, and I give IP address 10.1.1.1/24 under this interface. All this PC now use this virtual interface as a gateway. So I got a route in the routing table because of this virtual interface. My routing table will show like this: 10.1.1.0/24 is via VLAN 10. Likewise, when I create this another SVI bot, instead of 10, I put 20. (10.2.2.1). I get another route in my routing table, 10.2.2.0/24 VLAN 20. So this is what we will see in the routing table when we type show IP route. In some switches, you may need to type this command if you want routing. If the routing is not happening, you may need to type IP routing. Where? On the global configuration mode. See, you see the routing table, but it's not pinging. This is the reason. In some switches, you need to turn on the routing capability when you work on a multi-layer switch. By default, it is off. Right. Now, because you got the route in the routing table, when I ping from A to C, A and C are in two different VLAN. So site to site VPN, site to site VPN, site to site. All right. So what happens is the traffic from A, if I want to ping from A to C, the traffic from A will go to this interface. This interface is mapped to the SVI, and the routing table knows where is 10.2.2. It is in the other SVI called VLAN 20, so it forwards the traffic like this. I don't need a router here. This itself does the routing job. How do we configure it? This is how the configuration goes. IP routing, interface VLAN. This is what called as SVI, switched virtual interface. We give an IP address. That's it. If you want a routing protocol, you can enable routing protocol. This is how. In the global configuration mode, you type IP routing and you create the SVI. How? Interface VLAN. This is a command 10. VLAN ID is what? 10 for us. Give an IP address with subnet mask. You can also enable routing protocol if you want. So, inter-VLAN routing is very easy when we have multi-layer switch. We need not to jump between multiple devices. Right. So, routed port on a multi-layer switch. What is the routed port? Now, what we saw now is a VLAN interface. SVI is a VLAN interface, interface VLAN. Now, if I want to give an IP address, on the physical interface itself, on the multi-layer switch, I have an interface. See, this is the interface. For this interface, I want to give 10.3.3.1. I don't want to create SVI because I have only one interface in this subnet. See, here I have two interfaces, so I create an SVI, a common interface I create. But for 10.3.3, there is no reason of creating SVI. I have only one interface in that particular subnet. So no need to give a VLAN ID, no need to put it in a VLAN. I want to give an IP address. I want to make this interface as a layer 3 interface. See the difference. This is layer 2 interface. Because we don't assign any IP address on this fast Ethernet 0/1. We assign only on the interface VLAN. Now this scenario is different. We assign the IP address on the interface itself. This 10.3.3.1 I assign on the interface itself. Yes, ma'am. Correct. SVI is a logical interface. That's why we call it as SVI, switched virtual interface. It's a virtual interface that will be common for, if I say interface VLAN 10, it will be common for every interface that is a member of VLAN 10. That is one scenario. This another scenario is, I don't want to create SVI, I want to give IP address to the interface itself. Is there a possibility? Yes. All that you need to do is, you need to go to this interface. Let's say if it is fast Ethernet 0/5, you need to say no switch port. No switch port. By default, the ports are switch port. Layer 2 capability. They don't do any layer 3 operation. So what we do is, we go to the interface and say no switch port. You are no more a layer 2. When you say that, it becomes a routed port. It will start supporting all the IP commands. If you didn't say this, you cannot assign an IP address. It won't allow you to assign an IP address. When you say no switch port, it allows this physical interface to assign an IP address on where? On a switch. So you make what? You make the port as a routed port. Now the port is becoming a routed port. So a physical interface can be made as a routed port by typing no switch port. Whereas here, this is not a physical interface. This is a virtual interface called interface VLAN. So we also call it as VLAN interface. So on a multi-layer switch, you got two different type of interface. One, the physical interface is turned as a routed port. It can do routing. The other interface is the virtual interface, where The virtual interface will do routing for you. Because you got many interface belong to VLAN 10, you cannot assign IP address to a single interface. You need a common interface. That's why you create SVI. If there is no need of a common interface, you can straight away give IP address to the interface by turning it into a layer 3 capable switch port by typing no switch port command. Then you can give an IP address like this. You see IP routing and then no switch port to enable routing on the interface. Give an IP address with a mask, and if you want you can enable a routing protocol. So this is what the layer 3 capability on a multi-layer switch. Either you can have SVI or you can have routed port by typing no switch port. Now the next is about Ceph. There is something called Cisco Express Forwarding. Cisco Express Forwarding, Ceph. Ceph. Now Ceph is a very important entity in a layer 3 device. The Ceph is not only in a multi-layer switch, it is also there on a router. It is by default enabled, so people don't really realize that they have a Ceph. They don't even know, but a lot of people don't know that they have something called Ceph, Cisco Express Forwarding, which is there enabled on every router on Cisco. Even on a multi-layer switch, it is enabled. If you want to disable, you can disable it, but there is no advantage in disabling it. Ceph is good, that's why Cisco has enabled it by default. Now we are going to understand what it does really mean, Cisco Express Forwarding. Why we need this? What is the advantage? In any layer 3 device, if you see, there will be 3 planes actually. In the diagram they show only 2 planes. For a CCNP level understanding they speak, but when you come to higher level you will see one more plane called management plane. But anyway, we no need management plane here. Let's say now we got 2 plane, control plane and the data plane. See, you can easily understand the meaning of control plane and the data plane here. The control plane is the one which controls the routing process. That's what control plane. For example, if you take routing protocol, they only determine how the packet need to be forwarded, in what interface the packet should be sent out. So your packet is being controlled, your data flow is being controlled by the control plane. OSPF, EIGRP, RIP, they all contribute to a control plane. Right, now what about the data plane? Data plane is the one which forwards the packet, which moves the packet. Based on what? Based on the control plane information. So forward plane of the data plane and the control plane. See, the control plane is like a collector in an area. Collector, he gathers the information and then he analyzes thing, and he figure out where things are going wrong and where the things are right, and then he orders these local subordinates to act according to his command. So this local subordinates, the subordinates below collector, they are all like data plane. They are the one who executes based on what? Based on what the collector has commanded. So control plane is like a commander. Data plane is like an executor. So we got two different planes in a router, in a layer 3 device. So what happens is whenever a packet comes in, the incoming packet, whenever an IP packet comes in, the packet goes and checks the control plane, how I need to treat this packet. The control goes to the control plane and asks control plane, how should I treat this packet? Control plane will command, okay, do like this, send it via this interface. So control plane will do the control job based on the routing protocol information in the routing table. So based on that information, the data plane, what it does, it moves the packet. So if you see, there are two people involved, like two people, collector and the police department, executor, who executes the command given by the collector. Now every time whenever the problem comes, this police department calls collector even in the midnight and asks for for taking every step. They ask, they disturb collector. Can I do this? Can I do this? Can I do this? Now collector is fed up. So what collector does is, he says, okay, see, for this case, you do like this. First time he says that. For this case, you do like this. And also he says, if the same case comes again, do the same way. Don't come and ask me. Whenever this type of case comes, do this. He just gives instruction once. From the second time onwards, this data plane don't go to control plane. This data plane itself decides how I need to take steps, what type of action I need to take. So for every now and then, it is not going and disturbing the control plane. Only the first time a new case is coming, the police department official, they go and ask collector, how can I deal with this? He gives an instruction, this is how you need to do. That's all. From second time onwards, when the same similar case comes, the police department itself decides what action to take according to the experience they got in the previous case. By doing so, they don't disturb the control plane. So load on the control plane is reduced. Not only that, the decisions are made very fast. They need not to call the collector and wait for his response to take an action. So forwarding decision happens very quick if the data plane itself decides the outgoing IP packet. When an incoming packet comes, data plane itself decides how the packet should send out without disturbing the control plane. Initially it disturbed, later it identifies how the control plane will treat the packet. That pattern is there. Using the pattern, further packets are being forwarded. That pattern is what called as Ceph. That routing decision which was done in the control plane now is done in the data plane itself. So every time the packet is not going through the control plane, it is going based on Ceph information which is downloaded in data plane level. Ceph, Cisco CEF, Cisco Ceph, Cisco Express forwarding. So it makes the forwarding express, faster. Need not to go every time to the control plane. Control plane has given instruction. If this source comes, if it wants to go to this destination, go via this interface. That information is now stored in a data plane level. That stored area we call the Ceph, the algorithm which maintains the routing information, the control plane information down in a data plane, so that control plane can be bypassed from second time onwards, which quickens, which expresses the forwarding, is what called as Ceph. Hope it makes sense now. I'll show you. See, this is what Ceph diagram. A packet comes in. See, this is a router. A packet comes in. It is looking into the FEB table, forwarding information base. It is also a Ceph. Ceph, FEB, both are same. Now only the first time it goes to the layer 3 engine, which is a control plane, and finds the exit interface. And that routing information is now downloaded in the FEB table. When second time same source wants to go to the same destination, comes in, it will just see the FEB table, that is Ceph table, FEB, forwarding information base, which is also Ceph. So it will see a layer 2 next hop address in the adjacency table. So it knows which interface it needs to send it out. So it will go to the adjacency table, which has got the MAC information, MAC address information of the exit interface, and redirected like this without going through control plane, because the control plane information is already downloaded to the data plane level. This makes the forwarding quick, faster. Now I have skipped one slide. See, after this I skipped one slide. Let us see what this says. The layer 3 switching can occur in two different locations on a switch. One, centralized switching. The other one, distributed switching. Layer 3 switching can occur at two different locations. See, this talks about two different locations. The next one talks about two different methods. First of all, let us see how layer 3 switching can happen in two different locations. What are the locations? One is centralized switching. Switching decisions are made on the route process by central forwarding table. Next one is distributed switching. Switching decisions can be made on a port or a line card level. Now this may be too much for you to understand, but I'll make it very simple. This layer 3 switching means, the routing process, the routing decisions can be made based on the routing table, can also be made based on the port information. See, your routing table says go like this. A packet is coming, routing table says go like this. Do you think all the packet will go? No. If your access list is blocking on the interface, cannot go. So who controls there? Port. That is what called as a line card. Line card means, the ports are arranged in a line card. This is what called as a line card, where the ports are being arranged. So routing decision happens, layer 3 switching can occur at two different locations, centralized and distributed. Now let us talk about two different methods. One, route caching, another one, topology based switching. What is route caching? Caching means, what is caching? A buffer that maintains. Now route caching, what is it? For caching, what you need is a hardware. So you got a layer 3 route cache, means you have a chip where all your routing information, recent routing informations are being saved in a built-in hardware, which will see the traffic flow that is already stored in the cache memory and based on the information that is there in the cache memory, it will forward the traffic. But this is very old method. You know why? This cache memory has got a limitation. If the cache memory is full, no use. It won't have the latest updates. So cache memory gone out. And then came topology based switching. What is topology based switching? Again, same cache. Based on the topology, the information from the routing table is being used to populate the route cache regardless of traffic. So based on the routing table, the cache memory is filled. See, initially route cache is built based on the traffic. Who is going from where he is going to where he is going. Next is, it started referring to the routing table and building the cache memory. That is also worn out, again the same limitation, cache as the hardware limitation. It was not popular, and it will not get changed dynamically. Whenever the route changes in the routing table, cache will take a lot of time to get it updated. That is again another drawback. Then came the Ceph. Ceph is very dynamic. Whenever the engine, layer 3 engine gets updated immediately, Feb also will get updated very quickly. And Ceph is built based on the traffic information plus the routing table information. So Ceph has got combination of these two, and it's not a hardware level. It is not a hardware level. It is not a cache. It's a software level. So it can quickly refresh. That's why we have Ceph. So there is no more route cache or topology based switching. We got Ceph. And we already discussed what Ceph is. Yes, ma'am. No, not similar. See, the first one is not referring the routing table to build the Ceph, to build the cache. It is just seeing how the packet is being sent. Traffic flow. It is seeing only the traffic flow to build the cache. Now this topology based switching is not seeing the flow, it sees only the routing table and build the route cache regardless of traffic. It is not seeing the traffic. And again, both are hardware dependent. Hardware dependent means, if your cache is full, it won't get refreshed so soon. You need to reload, only then it will become empty. So when cache is full, whenever there is a new thing comes or whenever a change happens, the change will not get updated. But Ceph is software based, Cisco Express Forwarding, and it can quickly dynamically change according to the change that happens in topology. So it can understand very well traffic as well as it can understand your control plane. So this is more good. So that's what you also see here. Some IP packet cannot be processed in hardware. If the IP packets cannot be processed in hardware, it is processed by layer 3 engine. So okay, this is different thing. What it says is, in case if Ceph doesn't have any information, only then the packet will go through control plane. What we saw is Ceph is downloading the routing information, the control plane decision in a data plane. What if there is no information? There is a new traffic coming, fresh traffic. The packet comes in, checks the Fab table, no information. What it will do? Go to layer 3, ask him, control plane, what should I do? Control plane will say, do like this. So that information is downloaded and the packet will be forwarded according to that way. And when the second packet comes, it will not send it to the control plane. It will just send based on the Fab table. So only data plane moves the packet. So this is what about Ceph. Not necessary all this. These are all head breaking stuff, not much important. So if you want to disable Ceph, you need to type no IP Ceph. By default, Ceph is enabled. If someone disables it, how you will enable? Type IP Ceph. It enables Ceph. And if you want to see the Ceph table, type show Ceph. Show IP Ceph. Show IP Ceph. Show IP Ceph detail. These are all the commands. If you want to see the adjacency table for interface fast Ethernet 0/1 alone, you can type show adjacency fast Ethernet 0/1. If you want to see the Ceph only for fast Ethernet 0/1, you can use this command. To enable, this is the command. If you want to enable Ceph only for SVI, only for VLAN interface, SVI, IP route Ceph cache. Sorry, IP route cache Ceph. But the good news is Ceph is already enabled. This is just good to know topic. We are not going to do anything with Ceph in this level. When you go to MPLS Ceph is very important, which we learn in CCIE, MPLS, multi-protocol label switching. If you will be in a routing switching CCIE, you will definitely learn MPLS, or if you will be in a service provider CCIE, you will be definitely learning MPLS. Ceph is very important for MPLS. Now, here they have shown an example how to enable Ceph in a particular switch. And here, this is 4000 series. In the 4000 series, you enable Ceph under the interface level like this. In 3550 for SVI, you enable like this for the VLAN interface. So when I type show IP Ceph VLAN 11 detail, it shows that for VLAN level IP Ceph with switching is enabled. All right, more than this, which is more nice to see, is it's the same thing what I explained in the beginning. There is a command called show IP Ceph that will give you more nice output. So whenever you do some lab, I want you to type show IP Ceph. Whenever you do some lab in your packet tracer or in your GNS3, show IP Ceph. You don't need to enable, it is already there enabled. You will learn a lot there. Alright, if you want to debug Ceph, you can say debug IP Ceph. Not necessary, right? So in this chapter we learned about two things. One about Ceph, and then the previous story before Ceph. Before Ceph, we were having topology based switching, and then we were having cache based switching, and so on. The previous discussion was about Inter-VLAN routing using interface VLAN called SVI, switch virtual interface. Now there are 3 protocols which supports layer 3 redundancy. Layer 3 redundancy. What is redundancy? Redundant. Layer 3 redundancy. Meaning, I can also say it as gateway redundancy, to be more precise, gateway redundancy. Now what it really means, layer 3 redundancy. As I talk about this topic, I remember that I left one topic. Before I come here, I need to teach the topic. We will finish it now. Called PortChannel. Very important topic. PortChannel. I should have taken this topic soon after spanning tree topic. After spanning tree, I should have taken this topic. I forgot. Port channel. All that is necessary for your production environment, means in a real world, I definitely cover in my course. I don't leave those topics. All that is very important, necessary. This is very, very important. And even the HSRP, VRRP, GLBP, the layer 3 redundancy, which we will be seeing in the next class, that is also very important for your exam as well as for your real world production scenarios. Now, what is port channel? Port channel. See, whenever we have some redundant links like this, I got 1, I got 2. There are 2 links I have. Let's say this link is 10 GB and this link is 10 GB link. Do we have 10 GB links? Yes. Yes. Yeah, 1 GB link, 10 GB link. Fast Ethernet is just 100 Mbps. You got 1000 Mbps, which is 1 GB. You also got 10,000 Mbps, which is 10 GB. Now I got 2 10 GB links between switch 1 and switch 2. I got 2 10 Mbps link between switch 1 and switch 2. Now I have a question for you. Any one of you can answer. How many GB throughput will be there between this switch? How many GB throughput will be there between this 2 switch? Anyone can answer. We are not allowed to use 20 Gbps because STP is going to block one of the port. Only one link will be active and only 10 Gbps you got. You will say what to do. If the block is removed, there will be a loop. Block is good, but you are not optimized, you are not using the bandwidth fully. You got 20 Gbps, but you are not able to use all 20. There is no optimum utilization. There is no complete resource utilization. You waste your resource. 20 Gbps, out of which only 10 has been used, the other 10 is idle. So only 10 Gbps you use, the other 10 is idle. Because of STP, you need to compromise now. Because STP is blocking to prevent the loop, you need to compromise with the throughput. Only 10 Gbps is allowed because of STP blocking. Now what port channel does is, it gives a good news for you. Port channel says, these switches are very bad, cunning switch. We should cheat those switches. How you can cheat is, you tell the switches that this is not 2 link, this is just 1 link. Tell the switch that, switch, this is not 2 link, this is 1 link. If you make this 2 link as 1 link, then both the links can be available for your usage. See, because they are seen as 2 links, because the switch see this 2 link as 2 separate link, it identifies loop. The BPDUs are sent via this link as well as this link. The BPD that goes like this comes back like this and forms loop. The BPD that goes like this will come like this and form loop. So bidirectional loop occurs. If these 2 links are going to be considered as 1 link, how many BPDU packet will be sent? Only 1 BPDU packet not separately on this interface, but these two interfaces will be collectively known as port channel interface, another logical interface collectively. So for this interface only one BPD will be sent. So switches will no more see these two interfaces 2, it will see as PO1, port channel 1. For one port, for one interface, one BPD. So the packet will not come back again, because here also port channel 1, it is receiving via port channel 1. It won't send the same packet via same port channel. These two interfaces are going to be considered as one. So whatever is coming like this will not be sent back via the same port channel, so there is no loop. Port channel is nothing but aggregation of links. You group these links together and make the switch to feel as if it is a single link. By doing so, you can fully utilize the bandwidth that is available in the bundle. But there is a condition. When you want to bundle the links should be of same kind. Meaning, if you have an access interface here, switch port mode access, this also need to be access. You cannot take one trunk port and another one access port and bundle. Both need to be trunk or both need to be an access. Both need to be same duplex, half duplex or full duplex. Both should be same. Both should be same speed or the conditions that is applied. So if both are of same type of interface, here I got gig and gig, 10 Gbps speed, and both are access links, access port, or both can be a trunk port. Similar, I can bundle as one logical interface. Now I bundle this side and I bundle this side. The PO interface, the port channel interface, a new interface called PO interface will be automatically created, and it will come like this. The PO interface will come like this between these two switches. It will come like this. Now it is not a single interface. Sorry, it is not a double interface. It is single interface. It's just single interface. Though it has got multiple interfaces, it is seen as one bundle, one logical interface. Now the port channel is up. Now this port channel can be statically up like this, meaning both the side I turn on the port channel command. I enable port channel, that comes up. The port channel, after you turn on, they also can negotiate and decide whether they can be a port channel or not. That is dynamic port channel. I just configure here port channel, configure here port channel, and I enable a protocol to decide whether to have port channel between this or not. See, there are two ways in which you can have port channel. One, by using a protocol, you can negotiate and form port channel. The other one, you say, hey, this is port channel, up, come up. No negotiation, I'm telling you, come up. So you say that on the both side. That is on mode. There is a mode called on. You do it on both the side, on, port channel is up. Because you said the port channel is up. It is not because of negotiation. There is another two mode. The one is because of LACP. There is a protocol called LACP, Link Aggregation Control Protocol. There is another protocol called PAGP. So this LACP is IEEE standard, which is seen on every vendor switch. PAGP is a Cisco proprietary. Two protocols, LACP and PAGP. Now LACP stands for link aggregation. See, there are two links. You do what? Aggregation. Link aggregation control protocol. PAGP stands for port aggregation. See, again the same meaning. Two ports you are aggregating. Port aggregation AG, aggregation protocol. Link aggregation control protocol, port aggregation protocol. LACP is industry standard. PAGP is Cisco proprietary. If you want to use protocol, and if that protocol is PAGP, then both the side you should have Cisco switches. Why? It's a Cisco proprietary. Now if I have a non-Cisco, one side Cisco, then you can go with LACP. In non-Cisco you enable LACP, the other side also you enable LACP, then the port channel comes up. So this is what port channel. Now in port channel there are, in both LACP and PAGP there are two different mode. In PAGP, you got desirable, dynamic desirable, and then auto. In LACP, you got active, and passive. What it means? So if I enable active here, what I enable is I enable LACP. This will actively negotiate with the other switch. Actively say, hey, let's form EtherChannel. For that, this side you should have either active or passive. You cannot have desirable or auto. Why? If you enable LACP, it should be on both sides. If you say desirable or auto, then you enable PAGP one side, LACP the other side. That is bad. Both the side you enable LACP, and both the side it can be active or one side active, one side passive. Don't put both the side passive. Both the side if you put passive, they won't form EtherChannel, because passive means they wait for the other participant to negotiate. One side active, one side passive is good, or both the side active is good, which means you enable industry standard port channel. If you want to go with Cisco proprietary PAGP, then one side you have auto, other side desirable, or both the side desirable. Don't have auto on both the side. Auto will not negotiate. They wait for the neighbor to negotiate. Is there any doubt? So the presentation video about this is there in our channel. I'll send you the link now. Please go through that and try doing. After you watch the video, try doing by yourself. And if you have any query, let me know in the next class. The next class we are going to discuss about layer 3 redundancy, where we will be discussing about hot standby routing protocol, HSRP, virtual route redundancy protocol, VRRP, gateway load balancing protocol, GLBP. So this is what our discussion is going to be tomorrow. If you find these videos in my channel, yeah, we do have, go through that also and come. It will be easy for you to understand. Alright, if you don't have doubt, we'll stop, or if you have doubt, you can ask me any questions.